Now let us look at a related frequency response. This is the notch filter, and the starting point of the notch filter is this. Now let us consider h of z, which is 1 minus 2r cos theta z inverse plus r squared z to the minus 2. All we have done is we have inverted the previous example. We have taken the simple resonator, and this is the transfer function which is 1 over the previous transfer function, and hence poles become zeros and zeros become poles. So you had 2 poles here, they have now become zeros, and then the trivial second order 0 has become a second order trivial pole. And the response looks like this. So if you are on the unit circle, you will have a certain magnitude response. As you go across, since you are approaching this 0, the response will dip, will reach a minimum, and then again increase and have something like this. And it is very easy to see that the value of omega naught remains precisely the same. So this is indeed cos inverse, or rather 1 plus r squared by 2 r cos theta. Now based on the name notch filter, you expect the filter to actually completely eliminate a certain frequency. So for that to happen, you need to let r become 1. Therefore, if r equals 1, then what can you tell about omega naught? Omega naught becomes theta. So the picture corresponding to that is this. Now the zeros are on the unit circle, and the frequency response now has this shape, and this omega naught is now theta. And to such a system or to such a filter, if you applied an input which was cos omega naught n, then what will be the output? Output will be 0, because remember, response to cos omega naught n plus theta that we saw, output will be amplitude scaled and phase shifted, and the amplitude scaling will be the magnitude frequency response at that frequency. Here at that frequency the magnitude response is precisely 0. Therefore, if you apply cos omega naught n plus theta to this system, the output will be 0, and that is why this is called as a notch filter, because it notches out that particular frequency. But when you talk about notch filter, you also have an ideal reference. When we had low pass, high pass and other typical filters, we knew what the ideal low pass filter was, and then we had approximations to that. Now what will be the characteristic of an ideal notch filter? Ideal notch filter, if you want to notch out omega naught, at those frequencies the frequency response has to go to 0, but for any other frequency the response has to be ideal notch filter response has to be 1. So, it notches out omega naught, but for every other frequency the ideal notch filter's response will be 1. This is how the ideal notch filter's response is. It goes to 0 at plus and minus omega naught, and the response immediately comes back to 1 for every other frequency. And as you can see from this curve, this is far from ideal. It is far from ideal because as you go away from omega naught, the response does not rapidly come back to 1. Ideally it should instantly come back to 1, at least you want it to come back to 1 rapidly, and this is too slow. So, what can you think of based on what we have studied so far to make the gain come back to 1 as quickly as you can make it happen? That is, you want something like this. Yeah, very good. You want the gain to come back to 1, so you want to introduce poles now, all right. So, you have the notch filter and you want to introduce poles, and where do you want to introduce poles? Okay, it can't be outside because then if you are considering causality that won't work. So, it has to be inside, and then all right, same theta, and at what radius? Okay, so let us come visit that question. So, you want to place a pole at exactly the same angle and close to the 0. Now, in terms of transfer function, so the numerator, remember, as far as the notch filter goes, this is 1 minus 2r cos theta z inverse plus r squared z to the minus 2. For the notch filter, r equals 1. Therefore, without any other modification, the transfer function is 1 minus 2 cos theta z inverse plus z to the minus 2. All I have done is I have made r equal to 1, which is what it should be for the notch filter. Therefore, h of z is 1 minus 2, r is 1, therefore 2r cos theta becomes 2 cos theta z inverse plus r squared z to the minus 2, r is again 1, therefore this is z to the minus 2. But to make it better, you are going to introduce poles. So, you are going to introduce poles at r e to the plus and minus j theta, therefore it is 1 minus 2r cos theta z inverse plus r squared z to the minus 2. And geometrically also this makes sense, because if you are say at this point on the unit circle, then the distance between both pole and 0 is roughly the same. So, when you are reasonably far away from this point, wherever you are on the unit circle, to a good approximation, the distance to both poles and zeros is roughly the same, and hence the ratio will be 1. Therefore, the magnitude response quickly rises to 1, and as you approach, it gets pulled down because of the 0. Now, in practice, what should be the value of r? As close to 1 as possible, very good. So, 0.9 is good, 0.595 is even better, 0.99 is very good, better than 0.95. If 0.99 is good, then 0.999 is even better, right? Then your computator will give you 0.9999. So, what is a good value? No, gain is 1, right? 0.99 you will get gain close to 1, 0.999 even better, right? No, you want the angle to be exactly the same. There's no, doesn't make any sense to vary the angle. Even if you vary the angle, we are not talking about the radius, right? No, for realizability, what you'll realize is you'll realize this difference equation. What you are having in mind is, if you want to consider the impulse response, and then if you want to convolve the impulse response, then you have to truncate the impulse response to some limit. But that's not how you implement IIR filters. IIR filters will always have infinite duration impulse response, and the way they are implemented is, in the time domain you will implement the difference equation. So you will write this as y of n equals all these terms, x of n minus 2 cos theta, x of n minus 1 plus x of n minus 2, and then you will have plus 2r cos theta y of n minus 1 minus y of n minus 2. So this is the difference equation you will implement in practice. So it does not depend on how quickly or how slowly the impulse response decays. So that's not an issue. So in practice, what value of R you choose is dictated by finite precision effects. Remember, never forget that you are going to use finite number of bits to represent these coefficients, and closer R is to 1, if you want to represent it more and more accurately, you need a lot more bits, and the more bits you have, the more expensive the system is going to become. So how close R can be to 1 depends on how many bits you have to play with, depends upon the cost of implementation. Quickly, to give you a feel for this, let us look at frequency response without the poles and with the poles. So let us make R to be, R is 1. Okay, we will worry about R when you look at the improved notch filter. So theta, let it be pi by 4. So now let us plot the simple notch filter's frequency response. So this is, you need only the numerator polynomial. So this is 1 minus 2 times cos theta plus r squared z to the minus 2, r is 1. So this is the numerator, and then denominator is 1, and then you want to evaluate this at 2000 points, and let us evaluate this for the whole frequency range between minus pi to pi. So this is the frequency response of a simple notch filter, and now let us plot this. So this is command called FFT shift. What this does is, there is, right now we have evaluated the response between 0 to 2 pi. What this will do is, it will help you to plot the same response between minus pi and pi. So that's all this command does. And now let us plot the frequency response. So this is between minus 999 to 1000. I have to divide by 2000, so that now the x axis is between minus half and plus half. I am normalizing, instead of plotting between minus pi and pi, I am plotting it between minus half to plus half, and then let me plot the absolute value of the frequency response. So this is how the response looks like, and theta is pi by 4. So pi by 4 by 2 pi is 1 over 8, 1 over 8 is 0.125. So the 0 occurs precisely at 0.125. So this occurs exactly at 0.125. So this is the simple notch filter. Say that again. Yeah, that's okay. As far as we are concerned, we are mainly interested in notching out. So the fact that the gain is much more than 1 brings out one more case against the simple notch filter, in that it is far from ideal. So the gain being much greater than 1 is a case against it, for its departure from ideality. Of course, at plus 0.125 and minus 0.125, the gain is exactly 0. Now, let us make the pole to be 0.9. So, each one so the numerator stays as it is. The denominator is now 1 minus 2r cos theta plus r squared z to the minus 2. So, this is the denominator. So, denominator has now been, is not just 1, it is now the poles at r e to the plus and minus j theta, where r is 0.9. Now, let us make this to be 0.99. So, this is H2 and H2 is F50 shift H2. So, now let me plot all three. So, this is what you already seen. On top of that, I will also plot H1 and H2, and remember H1 is 0.9, H2 is 0.99. So, the red one is 0.9 and the orange is 0.99. So, clearly you see the huge improvement in the frequency response, right. So, this is 0.99 is so much closer to the ideal notch filter. The notch exactly occurs at the same point as it should be, but when you go away from the notch, the response becomes so much better when you place the pole closer and closer. So, this very nicely illustrates the effect of adding the pole to boost the gain when you go away from the notch.